Welcome. Today we're going to take a look at how to take derivatives of polynomials using the power rule. In physics, we take derivatives to get numbers. That gives us the actual slope of the tangent line at a point. And we also take derivatives to get functions. And we're going to see how that works both ways today. All right, so here we have a function y is equal to a, x to the n. A and n are just constants, just numbers. A is the coefficient and n is the exponent. And the power rule works like this. The derivative, and one notation of the derivative is saying y prime. So the derivative of y is equal to the following. So you're going to take the exponent, which is n, and multiply it times the coefficient. So you're going to get a times n out front. The x is going to still be there, but we're going to decrease the exponent by one whole number. Whatever n is, you're going to decrease it by one whole number. And there it is. That's it. That's how you take the derivative of a simple polynomial. All right. So let's see how that might work in practice. Let's do an example here. We have y is equal to 3x squared. Okay, so first step is you take the exponent and multiply the coefficient by that exponent. So y prime is equal to 6x, and let's just show it explicitly. 2 minus 1, right? So that is obviously equal to 6x to the first. Usually mathematicians are lazy and they don't write the exponent of 1. So 6x becomes our derivative. So now we can do it again, actually, and so we'll see what it looks like when we're taking the derivative of a number that has an exponent of 1. So we have the derivative is equal to 6x. Let's write in the exponent explicitly. It's x to the first. All right, and we're going to take the second derivative. So one notation for the second derivative is y double prime. That was Lagrange's notation, by the way. And so again, we're going to take the exponent, boom, multiply the coefficient by the exponent, so we get 6, and x to the 0 now. And again, mathematicians are lazy. They don't usually write x to the 0 since it's equal to 1, so we end up with the second derivative of 6. And let's take the derivative again. This is the triple derivative, y triple prime in that notation. And then again, 6x to the 0. And the rule works the same. So, whoops, that is not the third derivative. We're going to take it. So the rule works the same. It's exponent times coefficient. So 0 times 6 is 0. X to the negative 1 now. But anything times 0 is 0, and we end up with 0. Which is a pretty standard rule. You're trying to take the derivative of a constant. What is the rate of change of a constant? 0. It doesn't change. It doesn't have a slope. This would be a horizontal line on a graph, right? And remember, the derivative gives you the slope of a tangent line. Slope of a horizontal line is 0. Okay? So the derivative of any constant is going to be 0. The derivative of pi would be 0. All right? The derivative of square root of 2 would be 0. Okay? So that's something to remember. So the power rule here is going to work for any polynomial or anything we can write as a polynomial. All right, so this at first does not look like a polynomial until we write it as 4 times t to the negative 2. All right, so now, hey, we can use the power rule to take this derivative even though the exponent is negative. I'll show you the other notation for taking the derivative, dr dt. This was Gottfried Leibniz's notation, and it's very useful in a lot of instances. Again, we're going to take the exponent, multiply the coefficient by it. We get negative 8t. Now it's t to the negative 3. That would be the first derivative. We can do it again. The second derivative in this notation is d squared r dt squared. Sometimes I screw that up. Second derivative, and we do it again. Negative 3 times negative 8. We now have 24t to the negative 4. And we can keep doing this all night long. And I invite you to, if you got nothing else to do, take the 23rd derivative and see where it gets you. And I should probably mention with this notation, with Leibniz's notation, the thing on the top, that's basically the name of the function, right? Our function was r. And the thing on the bottom, that is the thing, the variable that we are taking the derivative with respect to. All right? So if we have multiple variables, different variables in a problem, and we're doing dr dt, then we're only going to be taking the derivative with respect to that variable. We're going to assume anything else in that equation is not changing. All right? And potentially we're going to see what that looks like in a bit. So now what if a polynomial has multiple terms in it, like this one does? We have 3 terms. The lovely thing about the power rule is it applies to each term individually. So we just take the derivative, apply the power rule to each term individually. So v prime is going to equal 3 times negative 2. We're looking at negative 6t squared. And then moving on, we have 2 times negative 8. That's negative 16 t to the first. I won't write the first. Plus the derivative of any constant is 0. All right, so we end up with v prime is equal to negative 6t squared minus 16t. We can do it again. V double prime is going to be negative 12t to the first minus, remember, this is t to the first here. 1 times negative 16 is negative 16t to the 0. T to the 0 is 1. So there we end up with our second derivative of this function. You might well be asking yourself, hey, does the power rule work to take the derivative of square root functions? It certainly does, as long as we write that square root as a power, r to the 1/2, right? So we're going to say dp dr, because we're taking the derivative of the function p with respect to r, is going to equal, again, exponent times the coefficient out front. 1/2 times 1/2 is 1/4. And now we're going to subtract 1 from our exponent. So 1/2 minus 1, we're looking at negative 1/2. Rewriting this, we're maybe looking at 1 over 4 root r. Not necessarily super pretty. I'd actually prefer to just leave it like that, because I can do everything I need to in that notation. All right? Like, for instance, what can I do by leaving it in that notation? I can take the second derivative. D squared p dr squared is equal to, again, exponent times the coefficient, negative 1/8 times r to the negative 3/2 now. All right? And again, we can keep doing this as long as we want. What about this function, which again doesn't look like a polynomial until we kind of simplify it, right? It's really 3x squared divided by x, which simplifies to 3x. And then it's negative 2 divided by x, which is negative 2 over x. But let's rewrite that so we can use the power rule, 3x minus 2x to the negative 1. All right, now we can take the power rule, y prime is equal to 3, I forgot my squared. My squared went away. 2 times 3 is 6. 6x to the first. Negative 1 times negative 2 gives us a plus 2. X, negative 1 minus 1 is negative 2. All right? So if at first it doesn't look like a polynomial, do some simplification so it does look like a polynomial. And sorry, I forgot my prime right there. Oh no, that wasn't the prime. Never mind, because that was still just rewriting the function. Okay, now let's take a look at finding a numerical derivative, because up to this point we've only looked at taking the derivative to give us another equation, another function. All right, so what would a numerical derivative look like? And remember that, again, we're going to use this to find the slope of the tangent line of a function at a certain point. So let's go negative 1/2 t cubed minus 3t, and we want to find the derivative at 2, just to make the arithmetic easy, since I'm not so good at arithmetic. So what is the slope of the tangent line? What is the numerical derivative of this function at time 2? All right, so we go x prime is equal to 3 times negative 1/2 is negative 3/2 t squared. Exponent goes down by 1 minus, that's 3t to the first. Remember, 1 times 3 is 3. T to the 0 is 1. So we just end up with 3. And now all you got to do, x prime at 2, you just plug in 2. Negative 3/2 times 2 squared minus 3. And I won't embarrass myself by making arithmetic mistakes any further. All right? Okay, so the last thing, and I promise, here we have a function that just looks like it's got a whole bunch of variables in it, and it's true that it does. All right, we're going to take the derivative of this function just with respect to one variable. All right, we're going to treat everything else in there as a constant. Okay, so we're going to do df dr. So we're taking the derivative of function f with respect to variable r. That means anything else in there we're going to treat as a constant. K is a constant, q1 is a constant, q2 is a constant. I don't even care at this point what they are. It is an equation from electricity and magnetism if you want to look it up. So let's rewrite this so we can use the power rule. K, q1, q2, r to the negative 2. Sorry. And sorry, we're not actually, that is not the derivative. We just reorganized it so we could take the derivative. So let's actually take the derivative now. df dr is equal to, let's see, we're going to take the coefficient and multiply it by all of the stuff out front. Sorry, that's the exponent. Multiply it by all the stuff out front. So the k is not going anywhere. q1, q2, they're not going anywhere. We just have negative 2 times k times q1 times q2. Okay, and our exponent goes down by 1, which is going to give us r to the negative 3rd power. All right, so we just took the derivative. We just used the power rule for r. Okay, k and q1 and q2 didn't change at all. All right, so this is again where Leibniz's notation comes in handy because it tells me what variable I'm really taking the derivative with respect to. Okay. We could feasibly take the derivative with respect to q1 if we wanted to, and everything else stays a constant. Okay, so that's why you got to pay attention to whatever that variable is on the bottom. That's it for now. See you next time.